can mutations really create novel adaptations? G'day, Ken Coulson back here at Creation Folding. Good to be with you. Look, if you haven't watched the previous part, then I would suggest that you go back and watch that. There's a lot of information there, and you may get lost as we go on here, although I'll try and reiterate at least a little bit. So what I want to do in this section is I want to have a look at the benefits of this conceptual morphospace model that I've outlined and its relationship to a creation model in general, speaking specifically in terms of morphology. So I'm going to go through a few things that have to do with biological morphology. Sometimes it will impinge upon the conceptual morphospace model that I propose. Sometimes it won't, but I want to sort of put it all together in a creation model that helps explain biological morphology and change. So in this slide, you'll see the words special creation on the left, Darwinian evolution on the right, the word solves in the middle. And the point being, I want to apply the conceptual morphospace model that I've looked at. I want to apply it to a special creation model on biological change and morphology in general. So I'm not going to talk about DNA, for example, because it doesn't have to do specifically with morphology. Although I think that the conceptual morphospace model does impinge upon that, and I think it's helpful. I want to focus more on sort of macro changes in morphology. And I want then to compare the same aspect with special creation and Darwinian evolution to see which aspect is more superior. So the first thing I want to look at is continuity. Now, I've already looked at this in the previous part, and that is that there is continuity between organisms, and we look specifically at these organisms, which are Sinosauropteryx, Archaeopteryx. This is Confuciusornis, and over here is a bird. And certainly you can see some real continuity in these three organisms, although I think there's continuity that exists all through these organisms. And yet, from a creationist perspective, these organisms were all created on days 5 and 6 of creation week, but they're all separate created kinds. And as I explained in the previous part, appealing to functionalism and appealing to sort of common design, it doesn't answer the question as to why you have that continuity. Whilst Darwinian evolution does and is able to explain continuity in terms of common descent. It just simply says, well, the Sinosauropteryx was the basic, that was the basic plan, and it was upon that plan that natural selection and other mechanisms came into play, and so we evolved the Archaeopteryx, and then we evolved the Confuciusornis, and then we evolved the bird, and so that explains the continuity. And that's a good way of explaining continuity. And that is why I want to talk about continuity in terms of the conceptual morphospace model, because that explains the continuity. I think prior to this time, I haven't really seen a good explanation for why we have continuity in both alive or extant living organisms and in fossil organisms. Why do we have that continuity? Well, this model, this conceptual morphospace model, explains that continuity. Now, that's not to say that the Darwinian evolutionary model is a bad one. I think both of them now have a good explanation for continuity. But it also solves discontinuity among fossil organisms. This is something that I don't think Darwinian evolution is really able to explain. Not very well, anyway. From a Darwinian evolutionary perspective, everything has a common ancestor. And that means everything has continuity. So you would expect to see great levels of continuity in the fossil record. And of course you don't, as I'll show shortly. And of course, discontinuity in the fossil record has been the mainstay really of creationist apologetics. Look, check out all that discontinuity in the fossil record. Hey, that's great proof for creationism. And of course, they really then just don't talk about those organisms that have continuity. So if we apply the conceptual morphospace model, that explains the continuity as well as the discontinuity. So from a creationist perspective, of course you would have discontinuity and continuity. You would have continuity because in the conceptual morphospace model, let's say God chose to bring just these organisms into existence, So there's 1, 2, 3, 4, 5, 6. Well, those 6 organisms are closely related in conceptual morphospace, and those organisms also share a lot of continuity. And so you would expect to see that continuity as those organisms are actualized in real life. But God is not committed to bringing just groups of organisms into existence during creation week. He may choose, for example, just to bring single organisms into existence. So he might bring this one, and he might bring just this one, and he might bring this one. Well, if he did that, those 3 organisms would show a lot of discontinuity between them. There wouldn't be any continuity, or very minimal continuity, that exists between those particular 3 groups, even though all of these would show great levels of continuity. So the conceptual morphospace model then answers the continuity, or sure, answers the discontinuity for sure, but it also answers the continuity. So for example, there's the Cambrian explosion, and I'm not going to get into this. You guys are more than likely familiar with that. You have 20, maybe as many as 40 different phyla, which is 40 different body plans that just sort of turn up in the Cambrian without any precursors or transitions. So how do you get 20 disparate, or maybe even 40 disparate body plans that just turn up with no precursors, no transitions? And no, the Ediacara biota, they just don't count. They're very, very different phylogenetically and morphologically, physiologically from the organisms that you see in the Cambrian. So how and where are those transitions? Well, that works perfectly well, as I've just explained, in a creation model. But it's not just the Cambrian explosion. There are other explosions of life or fossils that just appear in the fossil record. So for example, there's the Triassic explosion. So here's the Triassic. The Triassic explosion is where you see a whole bunch of really, really large organisms, as well as some other types of organisms that just appear in the Triassic without any precursors, or without any really good precursors or persuasive precursors. So for example, you get placodonts, you get nothosaurs, plesiosaurs, this and ichthyosaur, turtles, dinosaurs, pseudotsuchians, crocodilians. This is a pterosaur. You get hexagonal corals, and you get other smaller single-celled protozoan organisms as well that just sort of turn up out of nowhere in the fossil record. And in fact, we looked at this one, the ichthyosaur, a couple of weeks ago, where I interviewed Matt McLean. I'll put the link in the description if you want to watch that, where we saw that this actual line of descent, and that's what this means, where they first appear in the fossil record, actually goes right down to the Triassic Permian boundary. So in evolutionary science, the Permian, the end of the Permian, represents what they call the end Permian mass extinction event, where 95% of all life gets wiped out. And hence that's their explanation for why all these new organisms appear. They're sort of all taking up new niches because all those niches have gone out of existence because they all went extinct. But if that's the case, then where are all the transitions? Where are all the really good transitions, I should say? Take the ichthyosaur, for example. We talked about that with Dr. Matt McLean. I mean, this thing looks like it's really designed for living in the oceans. But it supposedly evolved from some kind of lizard or reptile, like a fully quadruped, land-dwelling reptilian creature that lived on the land, supposedly evolved into this fully marine creature. Well, where's the transitions? Why don't we find them? And this one's really interesting because now we've found ichthyosaur fossils that go right down to the boundary, which means that this creature must have evolved, if evolution is true, in the Paleozoic. Well, where are all the fossils? Well, they're not there. And you can look at other creatures as well, like a turtle. I mean, it's a very unique, complex creature, yet there are no really good precursors of fossils in the geologic record. Look at pterosaurs. I mean, this thing is designed to fly, yet it just appears fully formed in the fossil record. And there are lots of these in the Triassic. There's more than just these creatures here. So this doesn't fit in a Darwinian evolutionary perspective, but it does fit in the conceptual morphospace model, because you would expect to find discontinuity, like you see here, but you would also expect to see continuity. So it works. So I put an X there because I don't think that the evidence really explains discontinuity in the fossil record. Now, there are rescue devices. So, for example, punctuated equilibrium, acceptations, which we're actually going to look at shortly, evo, devo, other ways of explaining really, really rapid evolution in order to produce these creatures without leaving a fossil record. But I think that a lot of those rescue devices, they're ad hoc they're trying to explain the data, right? They see discontinuity, and so they can't accept a special creation model, so therefore let's come up with an explanation that works. So I don't think it works. Diversification, what some people call microevolution. Don't like the terms micro or macroevolution, but diversification, certainly that's a form of morphology, and I think it works in a special creation model because if we accept the scriptures as they've been written, then we do believe in a real curse that affected the entire planet. And you can go back and watch the previous part where I showed from the scriptures that certainly certain biological forms did actually change, it seems, supernaturally and by fiat because of the curse. It would make sense then, using that as an analogy for all organisms, that maybe all of the organisms on Earth were cursed, and certainly that would be true for predation. So in order for these animals that originally were vegetarian to become predators, you would have to change claws, you would have to change jaws, you would have to change teeth, and lots of other things would have to change. So I think what you're seeing there is a very real fiat change, as Francis Schaeffer says. Go back again and watch the other part, where these organisms are cursed and changed, where the earth then takes on that vanity that Paul talks about in Romans 8. Why? In hope, right? So God does this. He curses the earth because of man's sin, but it's done in hope to bring man to Christ, and then all of the creation is going to be redeemed, as Paul talks about in Romans chapter 8. Now, as it turns out, microevolution is perfectly valid in a Darwinian evolutionary model as well. I think there's been lots of good scientific papers out there that show that this kind of change, microevolutionary change, is true. We see it. I think it's a fact. So adaptation or diversification, it fits perfectly well in a special creation model, as it does in a Darwinian evolutionary model. Of course, in their model, that microevolution actually turns out to be extrapolated in order to answer the question and to provide a basis for macroevolution and from full-on evolution from a common ancestor. Okay, next one is macro changes in form. So this is why is it we have disparate organisms? Why is there such great disparity in living organisms? We talked about that with fossil forms, but why is there in living forms? And I would just say, again, special creation answers that, because that's what happened. God created disparate organisms. He created organisms that have some continuity. He created other organisms that don't have continuity. So the changes that we see are because of special creation. Now, from a Darwinian perspective, I don't think that they're really able to answer that question. And the reason is they don't know what the mechanism is for this huge macro change. I mean, how do you get complex organs? How do you get complex systems, organizational systems, working together? How do you get an eye? How do you get flight in birds? Using natural selection. Well, Darwinian evolutionists know that natural selection, it just doesn't cut it. They realize that natural selection does produce change, but they know that other mechanisms need to be incorporated in order to answer the question about macroevolution. And yet, these other mechanisms like evo-devo, exaptation, punctuated equilibrium, these are hypotheses, and they have some examples that work, as we'll see. But then those examples are really extrapolated and I think stretched and strained in order to fit the model. So I don't think that macroevolution has an adequate mechanism from a Darwinian evolutionary perspective, because remember, things can't look forward, things can't be mediated by design, you can't have any of that. Everything has to come about purely by random accidents. Okay, so I want to talk about one of these rescue devices called co-option and exaptations. And this one's important, I think, for a creation model, because I think there are aspects of this that have not really been answered well in creation circles. And I think that Darwinian evolutionary perspective, they've used exaptations and co-option in a very profitable way and a very persuasive way. So I think that creationists really need to drill down on this, but I also think that the conceptual morphospace model really answers this one as well. So first of all, let's look at acceptations. What are they? So if you have a look at the picture, you can see that this Irish elk, which is now extinct, had absolutely massive antlers. In fact, those antlers weighed about 35 kgs, which is about 80 pounds for you Americans out there. But its head only weighed 2 kilograms. It's not much, like 5 pounds, right? And so evolutionists they hypothesize that because these antlers were so heavy, over time, the vertebrae in the back, the processes on the vertebrae, and especially the neural spine, began to enlarge in order to have more surface area for muscle attachment to keep that head up. And that caused the organism to get a hump. And they then hypothesize that certain lady elks happened to like this hump on the back of bloke elks and decided, hey, I like that, I'll have a bit of that. And so they would then want to mate with these particular elks. Well, of course, if that's the case, then according to sexual selection, that trait, all right, would be passed on. It would be the trait that in populations, it would be the trait that survives. So eventually what you get is elks with larger and larger humps on their back because of sexual selection. And so that means then that essentially the hump sort of got co-opted. So rather than performing a function of holding up the head, it's now performing another function. And that function has to do with sexual selection. So the hump gets bigger now, not because of the growing elk's horns. It gets bigger because of its co-opted function under sexual selection. And I don't know if that story's correct or not, but you know what? It makes sense to me, and I've got no problems with that aspect of co-option, and no problem with that hump being an acceptation in that sense. But trying to extrapolate co-option from this very, very simple example to something like an eye or flight, that's another story, as I'll talk about now. So and we're going to talk specifically about flight. So birds need dozens and dozens of different kinds of adaptations in order to fly. They need all kinds of adaptations in their bones. Of course, they need all sorts of adaptations in feathers, in muscles, in their respiratory system, in their neck bones, in their behavior. I mean, lots and lots of parts in birds are specifically adapted, it would seem, for flight. So, of course, how do you do that in terms of a materialistic universe where there is no intelligent agent who's actually causing that process to occur? So evolutionists then turn to co-option as an answer. And so what they suggest is they look at the fossil record and they say, well, have a look. Here is Coelophysis, which is one of the basal sort of theropods. Here is Allosaurus, a little bit more evolved. And allosaurs, you can think of those sort of like T-Rex. They look a little bit like T-Rex. I mean, they're not, but they do look a bit like that. Of course, T-Rex only has 2 fingers. Allosaurs have 3. But anyway, this creature, you'll notice that in its carpal bones, it doesn't have this bone. And this bone is called a semilunate carpal bone, and it's essential for flight in birds. So here is a bird, and it has a semilunate carpal bone. So anyway, it doesn't have a semilunate carpal bone, but when you have a look at the fossils of Velociraptor, it does. Here's that semilunate carpal bone that you find in birds. Now, what's interesting is that Velociraptor didn't fly. It even had feathers, supposedly had feathers. I mean, even if it didn't have feathers, I think it did have feathers, the fact that it's got a semilunate carpal bone is really interesting. So that means that this creature had that semilunate carpal bone, and it was using that semilunate carpal bone for another purpose that wasn't related to flight. So this is, again, the evolutionary story. So then what happened when we get to Archaeopteryx, so more advanced, flyers, they co-opted the semilunate carpal bone from something like Velociraptor. They co-opted it along with feathers and other kinds of adaptations for the purpose of flying. So that's the way the story goes. But there are lots of problems with this, as I'll point out. The first problem has to do with functional mutations. What does that mean? Well, let me quote, first of all, Stephen Meyer. This is from Theistic Evolution, a Scientific, Philosophical, and Theological Critique. It's an excellent book, published in 2017. It is from Old Earth creationists, but I would advise reading it. Some good stuff in it. Anyway, he says this about getting a functional protein from mutation. He says, and speaking of, I think it's Douglas Axe, I'm not quite sure, but anyway, he says his experiments revealed that for every DNA sequence that generates a short functional protein fold of just 150 amino acids in length, there are 10 to the 77th power non-functional combinations. That's 10 to the 77th amino acid arrangements that will not fold into a stable three-dimensional protein structure capable of performing a biological function. So what he's saying is this: if you have 150 amino acids, you have a protein that's 150 amino acids in length, for every one sequence that's combination that actually produces a functional protein, you have 10 to the 77th power non-functional combinations. So for every one that works, that's how many you get that don't work. And here's the problem if we go back, okay, to this picture right here. So let's assume we're Allosaurus. And in the Allosaurus carpal bones, you've got multiple bones in here, and we want to produce a semilunate carpal bone. Well, in order to do that, there are literally hundreds and hundreds of genes in here that express cells, express other biological components, as well as instructions for how all of those parts go together. The problem is that somehow you've got to mutate a vast majority, or at least a great deal of those hundreds and hundreds of genes, and you've got to mutate them in such a way that they produce functional proteins that can then function in a different way to create a new trait. So think of it like this. If I'm an organism, and let's say as an organism in my life, I experience just 2 mutations. And let's say for argument's sake that both of those mutations happen to affect just the genes in these carpal bones. What's the chance they're going to produce a functional protein sequence? Well, of course, we've already seen that the chance is really, really low. Okay, so let's say we take not just one organism, let's take 10,000 of these organisms. And let's say all 10,000 of them experience 2 mutations in their life. What's the chance then? And let's just say, for argument's sake, that those 2 mutations actually affect, again, the genes in the carpal bones. What's the chance that those 2 mutations are going to affect that 150 amino acid long protein and create a combination that is going to, again, cause a functional protein to come into existence? Well, even with 10,000 organisms, the chances are really, really, really low. Okay, so now let's say that this organism lives for, I don't know, let's just say its range is a couple of million years in the fossil record. So this organism in its life experiences 2 mutations in the carpal bones, and let's say all 10,000 experience mutations in the carpal bones. And let's say that all 10,000 reproduce over 2 million years. So you have thousands and thousands now of generations of these organisms that all have 2 mutations in their carpal bones. What's the chance in that 2 million year period that those 2 mutations in each life over 2 million years and 10,000 organisms is going to produce useful proteins in those gene sequences? Well, according to the book that we just looked at and the quote by Stephen Meyer, the chances of that happening are really, really low. And of course, we're talking about simple adaptationism here. We're just talking about how do you get a novel feature, like, for example, a semilunate carpal bone. And of course, this has been a real problem in Darwinian evolution for, 80 years now. How do mutations produce novel features? And as far as I'm aware, that question hasn't really been answered completely. And so it hasn't even really been answered very well at all. And so that's a real problem in any kind of evolutionary model. But let's assume, just for argument's sake, that in fact these novel traits actually can come about through mutations and natural selection. Let's just assume that that's the case and go on from there. The next problem is the problem of trait directionality. So in the Darwinian evolutionary model, of course, you have a semilunate carpal bone that's evolving from something like this. But what's really interesting about this semilunate carpal bone is when you look at it, when you look at the Velociraptor and then the Archaeopteryx bone, and then you look at the same bone in Neornithes, which are just basically, think of that in terms of modern birds. The semilunate carpal bone does seem more adapt for better kinds of flight, stronger kinds of flight. In fact, all of the features in the modern bird would seem to suggest that it is designed for better, stronger kinds of flight than, for example, you find in Archaeopteryx. I mean, that doesn't mean that Archaeopteryx is primitive. It just means that the modern birds, what we consider to be modern birds, they do seem really, really well adapted for flight. The problem from an evolutionary perspective is that you should not expect to see any kind of directionality in these traits. See, there seems to be a direction here in which you have a semilunate carpal bone that is produced in an organism that doesn't fly, and yet this semilunate carpal bone seems to be modified, and seems to be modified in such a way that it seems to be better adapted for flight as you go in a direction. The problem with that is, from any kind of materialistic perspective, you can't have a teleological direction. You can't have any kind of final causation. Now, of course, the evolutionists will say, well, that's because that particular aspect is being modified over time and being adapted for birds. Well, here's the problem. The genes that are in the wrist should not only create adaptive traits like a semilunate carpal bone. In other words, it's completely random, right? It's accidental, which means that the wrist bones, the carpal bones, should create a combination of features and adaptations for all kinds of different situations. So what I would expect to see in a sequence like this is I would expect to see a whole bunch of different kinds of wrist type adaptations that have lots of different kinds of functions. And then co-option, if you like, sort of comes in and cherry picks the adaptation that suits it for flight. That's what you would expect if indeed this evolution is completely random and materialistic without having any teleology, without having any final causes in mind. But that's not what you see. Where are all these different adaptations, wrist adaptations, that should have also been produced along with our semilunate carpal bone? Where are all these other adaptations? Well, we don't see them. Now, someone might object and say, well, those organisms, although they had some kind of adaptation in the beginning, they just didn't do well, so they all died out. Okay, fair enough. Where are all the fossils? Where are all the fossils for all those different adaptations? So this is a real problem, that you see a very, very nice sequence here, which you should not expect if indeed materialistic, random mutations and accidents are in fact producing an organism and adaptations that are going to cause an organism to fly. And it's not just the semilunate carpal bone, it's actually all of the different adaptations that are necessary for flight. So for example, look at the feather. So the feather's really, really complex. It has lots and lots of different parts. You've got a quill, you've got the shaft, you've got the veins, you've got the barbs, there's barbules on top of the barbs, and then there's little hooklets as well that all go together, as well as an asymmetrical form to cause a feather to be useful for flight. So in this diagram here for the evolution of the feather, this asymmetrical feather is a fully pennaceous feather that would be useful for flight. These other feathers would not be useful for powered flight, or they would be useful in some degree, but you certainly need this one. You certainly have to have an asymmetrical pennaceous feather for flight. Well, here's the problem. If, once again, we suppose that all of the different genes involved in creating the feather, and we're talking again about hundreds and hundreds of different genes, if we suppose that mutation is able to take a majority of those genes, and it's able to cause those genes to change so that they have perform another function, and create workable proteins, and not only that, but of course workable timing sequences, if all of that is a given, and that actually happens, because this is random, you should expect all kinds of different feather structures. I mean, not just a nice sequence like this. You should expect literally dozens or hundreds of different kinds of adaptations that have lots and lots of different uses that have got nothing to do with flight. Now, I've just sort of scribbled down a couple of examples. So here, for example, is the shaft. I've just taken a shaft and I've made it into a squirrely looking thing. So what if each scale, for example, produced one of these kind of squirrely feathers, or at least feather shafts? And what if that was all over the organism? And what if that particular adaptation had a completely different function than, say, thermoregulation? I don't know what it is. I'm just coming up with ideas. Why didn't something like that also evolve? Remember, this is accidental. All of these genes are creating different kinds of adaptations that should be very, very variant in all different directions, because we're not thinking ahead. We're not thinking in terms of flight. We're not thinking in terms of a symmetrical feather, a symmetrical pennaceous feather. And here's another one. What if, say, two of these shafts, so here's a shaft here, here's a shaft here, what if they sort of joined together and formed a point? In fact, what if, say, 6 of them joined together and formed not just a point, but kind of a point that actually punctures skin, or that actually protects the animal? And let's say each of the scales got together and different shafts combined to produce points on the surface of the animal for the purpose of protection, for the adaptation that would help that animal in protection. Again, I'm just coming up with some examples, and I could come up creatively with all kinds of different morphologies for potential feathers. Well, where are they? As it turns out, this is what we have. And not only is this all we have, but this is actually a sequence. It looks directional. You start off with very simple shafts, and you add veins, and eventually you add barbules, and you add hooklets. And so it seems to have a direction that's leading, okay, to a goal or a final cause, which is a symmetrical feather. You would not expect that in any kind of materialistic, random system of mechanisms. So I think that this is a real problem for the idea of co-option, and that is this problem of trait directionality. Okay, the next thing is the problem of interdependent compatibility between co-opted traits. So, for example, here are just 3 traits that are required for flight. You have to have hollow bones, you have to have a semilunar carpal bone, and you have to have feathers. Now, of course, there are dozens and dozens of traits that are required for flight. There's lots of muscle attachments and tendons, and you have to have respiratory systems, and then you have to have coordinating systems so that everything coordinates. So there's lots that goes into this. So lots and lots of traits. Well, the thing is, okay, all of these traits are evolving, okay, on their own, separately, having different functions, and yet they're all supposed to come together and coordinate in a very precise way to produce flight. So I think that this problem of an interdependent compatibility between co-opted traits, you do see that, but you wouldn't expect that if this was purely materialistic without any intelligent agency involved. And then, of course, there's the problem of the order in the fossil record, and we've already looked at that. But if you look at, these are all different theropod groups. These are all different theropod groups that have feathers. And what's interesting, when we look at this group, which is Anchiornithidae, and this has Anchiornis in that group, and Anchiornis is the first organism that we see with feathers in the fossil record. In fact, there are no feathers that appear in the fossil record before this point, not even primitive forms. So all the primitive forms of feathers we saw in that sequence, they actually appear either in the same place in the fossil record, or they appear above that in the fossil record. So here's a real problem, because what you have is, you have hollow bones, you have semilunar carpal bones, you have fully formed panaceous feathers and flight, because apparently, according to this paper, which I showed you in the last part, according to this paper, Anchiornis actually had the ability, or might have had the ability, to fly. So now you have all the different parts required for flight. All of the different adaptations have come together in Anchiornis, allowing it to fly, but there's no fossil sequence leading to that full combination of parts. In fact, a lot of the parts that evolutionists use to try and support the idea of an evolving sequence actually appear above that in the fossil record. So if I go right back to this slide, and of course go back and watch part 2 for that. So for example here you've got Velociraptor, and here's Archaeopteryx. Well, of course, Archaeopteryx appears well before Velociraptor in the fossil record. And there are lots of other of those examples. Go back and watch part 2 for that. So when it comes to apparent acceptations and co-option, I don't think that works from a materialist perspective. There are too many issues involved in trying to take multiple dozens of traits and trying to, first of all, get the traits, get them adapted, get them there, and then cause the traits to work together and come together to form flight. I just don't think it works at all. Now, here's what's really important. And this is why I think that the conceptual morphospace model is crucial in a sort of a full-orbed creation, special creation model in general. And it has to do with co-option and homology. As it turns out, and this is just a quote from an old Earth creationist on that I saw on an Uncommon Descent post, and it's really interesting because this person who blogged this post attributes homology as being the main reason that evolutionists, or homology is one of the main reasons that evolutionists use to support co-option. So first of all, what is homology? Well, homology is, for example, if you take vertebrates, we all have a backbone. In the evolutionary model, there was an organism sometime in the past that possessed a backbone, and we, modern vertebrate animals, we simply share in that homologous trait. In other words, that's sort of the primitive trait, and that primitive trait is passed on, and so my backbone and the backbone of a dog and that of a horse, they're homologous because they all come from one common ancestor. That's what homology means. Well, listen to what this old Earth creationist says about homology. He says the evidence from homology which undergirds co-option hypotheses, okay, in other words, according to co-option hypotheses, homology is very important, and I'll get to this in a minute, was probably worth the mention, i.e., the similarities between the type 3 secretory system and the flagellum. And so there they're talking about co-option with the flagellum, all that ID sort of stuff. And what he's saying is that there are similarities between the secretory system, okay, and the flagellum. They have lots and lots of parts that are in common, and they do look very, very close to each other. So what he's saying is that this concept of homology, that there is some previous foundation which we see, and upon which the next level of evolution occurs. And so it's that previous foundation, it's that previous thing that leads the evolutionists to assume that co-option occurred. So he goes on to say, I've often noticed that the evidence presented for evolution is almost exclusively evidence for common descent rather than natural selection. That is, evolutionists point to extremely convincing evidence for natural relationships and then simply assert that the step from A to B was accomplished via variation and selection. Co-option is just another example of this. So for example, if we go back to this slide, so this is what we mean by homology. So, we find the Velociraptor skeleton, and it turns out that the Velociraptor skeleton has that semilunar carpal bone, but it doesn't fly. So the evolutionist says, well, look at this. This Velociraptor, it didn't fly, but it has a semilunar carpal bone, which birds have. So therefore, okay, because we see this homological trait in the past that wasn't used for flight, therefore that adaptation must have been co-opted for flight. And what that old earth creationist is saying is that this explanation becomes the foundational reason for believing in co-option. It doesn't matter that mutations don't produce workable adaptive proteins. It doesn't matter that there's directionality in the fossil record, that we don't see, dozens and dozens of other adaptations in lots of different directions that don't get chosen. It doesn't matter that there are all of these hurdles. What matters is, hey, we see this homological trait in the fossil record, which is in an organism that doesn't fly. Now it's in an organism that does fly. Therefore, it was co-opted. That is what he's saying. And that is something that creationists to date have not been able to answer adequately. And that's why we need, I think, some kind of conceptual morphospace model that's able to explain this problem from a creationist perspective. So you'll remember in the conceptual morphospace model, there's continuity. So here are our four organisms: Sinosauropteryx, Archaeopteryx, here is Confuciusornis, and here's a bird. And in morphospace, conceptual morphospace, all of these organisms are connected. There's continuity that exists between all of these organisms. But something else that's really important, and I did talk about it in the last section, go back for a more fuller discussion of it there, but I talked about the concept of biological organization. So, for example, we talked about organization of the human body. So in the human body, you have an atom, a molecule, a macromolecule, you have a organelle, you have a cell, tissues, organs, organ systems, and of course then an organism. Yet you can't take any one of these sections out of the sequence. It seems as though God has built organisms in an organizational way where you have some fundamental structure, and upon that fundamental structure, other structures are added so that you have a growing level of organization. You do see that in the human form, and you see that as well in reproduction. So organisms start off as single cells, and then they grow, they go through multiple iterations, right? An infinite number, really, of iterations until they reach their teleological goal, for which this cell already knew about and was looking ahead, pointing towards, and that is to get to an adult human being. So that concept of organization exists in reproduction as well, where there's a foundational structure, and different structures are built on that foundational structure until you get to that final cause, which is a mature human. So what I'm suggesting with the conceptual morphospace idea is the same kind of principle when God is putting it together, or when he is designing organisms. So for example, you have Sinosauropteryx up here. Well, Sinosauropteryx had hollow bones. Hollow bones are going to be essential in flight. And then you have this one. Let's just say for argument's sake that this one is Velociraptor. So now you have hollow bones, and now you have semilunate carpal bone, and you also have feathers. I do think that Velociraptor had feathers, but let's just say it didn't. Well, then you get over here to Confuciusornis, which has a semilunate carpal bone. It has feathers. It has the full ability to fly, and of course it has hollow bones. And then when you get over to the birds, you seem to have a designed organism that has the full suite of features available for extended, strong, powered flight, a bird. So what I'm suggesting is that in conceptual morphospace, there is a sense in which God has designed things in an organizational manner. So God, who creates Sinosauropteryx, and he creates Sinosauropteryx with hollow bones, and those hollow bones are adaptive and they're completely functional in that organism. But what I'm saying is those hollow bones are sort of a basic or foundational level of organization that will then look forward towards an ultimate final cause in what we would call modern birds, in that these organisms have the most powerful kind of flight. Now, it's not that Archaeopteryx was primitive and modern birds are modern. It's just that final cause, what we call modern birds, happen to be the best of all feathered flyers. In other words, they would have been better flyers than, for example, Confuciusornis. Yet Confuciusornis would have been a better flyer than, say, Archaeopteryx. And again, that has got nothing to do with primitive. It's got nothing to do with evolution. It's got to do with God's creative design. It's got to do with the way he wanted organisms to live in certain ecosystems. For example, Archaeopteryx may just have lived close to the ground in trees and been very, very isolated in a single forest. Yet maybe Confuciusornis was designed to fly longer distances. And of course, modern birds, they can fly huge and massive distances. It just has to do with God's creative design, what he wants out of each organism. Now, keeping all that in mind, we can approach this slide differently than an evolutionist does. So remember, the evolutionist, he sees the trait in the velociraptor that doesn't fly. He sees the same trait in Archaeopteryx that does, and in fact it may be just a little bit more adapted for flight in Archaeopteryx, as it certainly is in birds. And he says, oh, this trait here in Archaeopteryx was co-opted from some kind of more primitive velociraptor. Now, I've already given reasons why that just really can't work. There are lots of good reasons to reject that hypothesis. But in the conceptual morphospace model, this makes perfect sense because these adaptations are actually forward-looking. They have a direction. They're designs that look forward to the final goal or the final teleological end for flight, which is a very superior kind of flight in modern birds, which is in this organism here. So I think that that's something that, again, remember, all of this is a hypothesis, but I think it explains really well and does away with the excuse that evolutionists use when they look at homological parts. So they look at this, for example, at this semilunar carpal bone. They say, well, that's a homological part that was co-opted for flight. And we would say, sure, yeah, there's homology between these parts, but it's got nothing to do with evolution. It has to do with special design and teleology. And there's a couple of interesting quotes as well that I just want to finish off with here. So there's this one. This is from a philosopher of science, and I think it was written about the 60s or the 70s, maybe the 80s, something like that. Etienne Gilson. And if you get a chance, read this book. It's really, really interesting. But he's talking about the concept of teleology, that we can't escape the reality of teleology in nature. So this is actually not from Gilson. This is actually from the person who wrote the foreword. But he says this: the human mind can grasp only that which is intelligible. The development of a chain of living things in terms of some kind of unfolding or progress is certainly intelligible, by analogy to the development of any given complex organism from a simple seed or egg cell. But the meaning of absolutely directionless, meaningless, purposeless Darwinian change cannot be grasped. There is no meaning in such an alleged process, and thus no intelligibility. So what he's saying is, look, the idea of a chain, the idea of an unfolding chain of design that has a teleological end, in other words, very Aristotelian principle, right? It makes sense. It's intelligible. But the Darwinian concept of directionless, meaningless, purposeless change, it can't be grasped, and it's not intelligible. And I would say it's not only not intelligible, I would say that the evidence doesn't really point in that direction. Pardon the pun. Next is, this is actually a quote from Gilson, page 59, and this is actually, he's talking about Augustine. He says, Augustine in his school understood that everything that ever has been or would be had been created under a latent form, invisible since the time of creation, which took place in the twinkling of an eye. Since everything that developed came from that, we have here a true doctrine of evolution, understood in its natural sense of the unrolling or something already given. What he's saying is that the term evolution originally was a term that meant unrolling of something that's already latent. In other words, it was already, think about writing out information on a roll and rolling it up, and then you unroll it to reveal what was already written. That's actually the original definition for the term evolution. In fact, Darwin knew that, and he actually refrained from using the word evolution until his 6th edition of The Origin, and you can read that in the book here. So he didn't like the idea of evolution because it smacked of teleology, and that is that everything that we see around us, everything in nature, actually has an origin before anything even existed. In other words, it existed in the mind of God. The designs were all there. They just needed to be unraveled or unrolled. So I think that's really interesting and applicable to the conceptual morphospace model. And this one as well. And this is really important because if there is teleology in nature, this is what Coulson says, the theologian has the right to rely on this fact in order to draw from it the consequences which, in his eyes, proceed from it concerning the existence of God. And ultimately, this is what it all boils down to. You see, if there is teleology, if you can show directions with things, and you can show that those directions only work in some kind of intelligent design worldview, then you can bring up the concept of the existence of God. And of course, I think this is the reason why Darwinists hate teleology. They don't want to see direction in things, because if you see direction in designed things, that obviously smacks of God, something that is, of course, to be avoided in a materialistic worldview. And lastly, sort of going along with everything that has been said here, a quote from Paul Nelson, a philosopher of biology. He says, "Avian flight requires a cause that's able to visualize a distant endpoint and bring together everything necessary to achieve that endpoint. Only intelligence is capable of that kind of causal process." Now, of course, Paul Nelson, he's a creationist, but he's not thinking in terms of conceptual morphospace. He's never heard it before. But I think what he says really makes sense given a conceptual morphospace model, where flight, it does require a cause that's able to visualize. And of course, that visualization, when does that occur? Well, it must occur in eternity past, right? So in eternity past, there is a divine, intelligent cause that visualizes a distant endpoint and brings together everything, necessary to achieve that endpoint. And of course, in the conceptual morphospace model, it's not that these other organisms don't have an ultimate endpoint and a teleological end in and of themselves. It's just that when it comes, for example, to flight, there seems to be another level of teleological ends, in that God wants to fashion and design a creature that has a supreme level of flight, and that would be the modern bird. Okay, so I think that's it. I'm gonna call it quits there, because we've got 2 more things to cover, and that's convergence in the fossil record, and I'll cover those in the next part because we're just running out of time. We've already gone way over time as it is. So that's all from me, Ken Coulson here at Creation Unfolding. Again, look, hit that like button, please. You can subscribe, ring the bell for easy access as well for more videos as they pop up. There's a website. There's always more stuff there as well, www.creationunfolding.com. There's a book if you're interested, sort of talks about different areas of, or kind of a model for mature creationism. And of course, there is a donate button if you feel so inclined. And of course, look, as always, pray for me, okay? Just spend a few minutes, or even just a few seconds, and pray for me. I'd really appreciate it. Thank you and goodbye.